Hello students, welcome to today's video. In this video, we are going to study about charge distribution. Now, what is charge distribution? This charge distribution can be picturized in two ways. One is the macroscopic picture and the other is a macroscopic picture. Now, in the macroscopic picture, as you know, what is a microscope? It is an instrument to see very small objects. Okay. So, in the macroscopic picture, we take a very closer view of the charges. Now, in this picture, whatever we have already done, suppose we have done the Coulomb's law, then we have also studied the superposition principle. So, in all those theories, what we have done, we have just considered the charges to be discrete quantities. In this picture, we have to take the charges as Q1, Q2, Q3, Q4, Q5 in that way. Okay, so this is a discrete distribution of charge. We see the charges as separate entities or separate elementary particles. So we have written here that these charges are discrete in nature in the macroscopic picture. So in this picture, what we have done is we have also studied the quantization of charge. So what is quantization of charge? In the quantization of charge, according to quantization of charge, we know that a total charge on any conductor is the integral number of the charge on one electron. Now here n is an integer which can take values from 0, 1, 2, 3, 4, and E is the charge on one electron, that is 1.6 into 10 to the power minus 19 coulomb. Okay, so what we have seen here is the charge on any body or any conductor is the integral number of the charge on one electron. So this is a picture which we call macroscopic picture. So as we know that with our normal eyes we cannot exactly see the charges as they are very small particles or very small elementary particles. So we cannot see these charges as separate entities. So what we have to consider is we have to consider a collection of charges, and in that collection of charges we can see the charges from a very far point. Okay, so if we see the charges from a very far point, then these charges would appear to be continuous. So in this conductor, this is a conductor. In this conductor, I have drawn the charges to be a continuous distribution. So in this continuous distribution, we have considered the total charge on this conductor to be Q. So this is a macroscopic picture. Macroscopic means a larger view. Okay, so we have seen a very larger view compared to a macroscopic picture. In this picture, the charges are taken to be continuous. These charges are continuously distributed. Okay, so what we have written here is the charges are continuously distributed on this conductor. Now, as you know that in a non-conductor, the charges can reside inside this conductor because there are no free electrons, right? In conductors, what happens is the charge is uniformly distributed over the surface of a conductor. That means if we consider the conductor to be this one, then in this conductor the charges will be equally or uniformly distributed over the surface. The charges do not reside inside the surface of a conductor, right? So in a conductor, what we know is that the charges always resides on the surface of a conductor. And how these charges are distributed? They are uniformly distributed over the surface. Okay. So what we got here is a continuous distribution of charge. This is what we know charge distribution is. Now, the charge distribution on any conductor can be determined in three ways. First of all, we have to determine a parameter which is called the charge density. We consider here a parameter which is called charge density. Now, what is charge density? Charge density is charge per unit dimension. So here, if we take a one-dimensional object, then we will have to consider 1D, charge distribution on one dimension. Similarly, if we consider a conductor which is two-dimensional object, suppose a surface area, then for that surface area we will have to consider the two dimension, and in that case we will have to calculate the charge density. Similarly, for the 3D object, suppose a cube or a certain volume spherical object we can take. So for that three-dimensional object, what we will have to do? We have to study the charge distribution, and that charge distribution can be studied using a charge density per unit volume, where 3D is the volume. Okay, so what we have done is we will have to calculate a charge density, and how this is calculated? This is calculated by using the formula charge per unit dimension. That means it can be q by 1d if the object is a one-dimensional object, or if the conductor is a one-dimensional object, then we will have to consider q by 1d. Similarly, for if the object is a two-dimensional object, then what we will do? We will use this formula. This is q divided by 2d, or this concept. Similarly, for 3d, which is a volume, for the volume we use this formula q by 3d. This is three-dimensional. Okay. So for the first one, q by 1d, which is this is nothing but a line. Okay. This is nothing but a surface, and this is nothing but a volume. So if we divide the charge by the length, then what we will get? We will get the linear charge density. Similarly, if we divide the charge, total charge on the object or total charge on the conductor by the surface or by the area of the surface, then what we will get? We will get the surface charge density. Here, if we divide the total charge on the three-dimensional object or three-dimensional conductor by the total volume of the conductor, then what we will get? We will get the volume charge density. So here we have got to learn three things. One is the linear charge density, second is the surface charge density, and third is the volume charge density. Okay. So what we have seen here is we can study the distribution of charges in three ways using three parameters. What we have done here, we will now study the linear charge distribution. Now what is a linear charge distribution? It is suppose we consider conductor which is of one dimension. We consider a one-dimensional object. We can consider a pen in this case. This is its length is very large compared to its thickness or width. Okay, so this is a one-dimensional object. For the one-dimensional object, suppose on this object charges are equally distributed over the surface, right? So we have drawn the diagram here. Here we have taken a one-dimensional object whose length is L, and we have considered a uniform distribution of charge over its surface. And what is the total charge on the conductor? It's Q. Okay, Q is the total charge on this conductor. Now we'll have to calculate the linear charge density. How do we calculate? Just it is denoted by the letter lambda, right? So what is the linear charge density? It is nothing but the total charge on the body divided by its length, as we have said here. It's q divided by 1d. So what we will write here? Lambda equal to q divided by length, right? If we consider a very small part or a very small element of length of the conductor, if we consider a small length element of the conductor, here I have denoted it as delta L. Delta L is a small length element of the conductor. For this length element, and it got erased here. For this length element, we consider the total charge present in the element to be delta Q, right? So from here to here, for this length of the conductor, the total length is delta L, and the total charge present on this element is delta Q. So for this part of the conductor, for this element of the conductor, what we will get? We will get the linear charge density, and that will be equal to delta Q divided by delta L, right? Next, if we consider this length element to be very small, infinitesimally small, if this length element is infinitesimally small, and if the charge present in that part will also be very small, okay, in that case we will consider here dl, the length of the conductor, and the charge to be dq. Okay, we consider the small length element to be dl and the total charge present in that element to be dq. So what we will get? We will get the linear charge density denoted by the letter lambda, and this will be equal to dq divided by dl. Here dq is the charge present in that element of the conductor, and dl is the length of that small element of the conductor. Now if we cross multiply these two, then what we will get? We will get the total charge dq present in that part of the conductor or that element. So we just cross multiply these two, then what we will get? We will get dq is equal to lambda dl. Now what will be the unit of linear charge density? See, we have divided here the charge by one dimension. That means we have divided the total charge present in the conductor by its length. So for the charge we have the unit coulomb, and for the length we have meter. So what will be the unit of linear charge distribution? It will be coulomb per meter. Okay. Now we come to the next point, surface charge distribution. In order to determine the total charge present on the surface or a two-dimensional object, suppose a rectangle or a square, we may consider a conductor which is of a rectangular shape or a square shape, or any such surface such as a plate, a circular plate we may also consider. In that case, what will be the charge density? Now see, we are going to calculate the surface charge density. What will be the surface charge density? According to this formula, we will divide the total charge on the surface divided by its area. Okay, we divide the total charge present on the surface by the total area. If we consider this type of a surface, we consider here a surface where the charges, total charge delta Q is distributed uniformly over this surface. So what we have considered here? We have considered here a surface where charge Q is uniformly distributed over the surface. And what is the surface area of this part? The surface area is capital S. Okay, S is the surface area. So what will be the surface charge density? Similar to this formula, we have to divide Q divided by the area. The total charge is Q, and what was the surface area? It was S. So we have divided Q by S, and what we get is sigma, which is the surface charge density. Surface charge density is denoted by the letter sigma. Right. Similar to this case, what we have considered a small length element delta L. For the surface, for this surface, we consider a small area element, and the area element is we have considered here is delta S. For that area element delta S, we suppose the charge present in that area to be delta Q. Right? This is delta Q is the charge present in the surface area delta S. So what will be the surface charge density for this small area? For this small area element, it will be delta Q divided by delta S. And now if that area element is very small, if the area element is very small, then what we will consider? We will have to consider a very small surface area ds. Okay, so we have considered here ds, and what will be the charge present in that part? Since the surface area is very small, therefore the charge present in that area will be also very small, so we consider the charge to be dq. Right. So what we get here is the surface charge density according to this formula. We have divided dq by ds. This is sigma, which is the surface charge density. Now if we, similar to this case, if we cross multiply these two quantities, what we got? This formula. Similarly here, we cross multiply sigma and ds, and what we get is the total charge present in this small area element of the conductor. So we get dq is equal to sigma ds. What will be the unit of the surface charge distribution or surface charge density? The unit will be similar to this one. What we got here was, we have divided the charge by the length, unit of length. So here also similarly we get the charge here. This was the formula. We divide the charge which is whose unit is coulomb, and we divide that charge by the surface area. Now for the surface area, the unit is meter square. So what we get is coulomb per meter square. This is the unit of the surface charge density. The next thing what we will try to learn is the volume charge distribution. For volume charge distribution, we consider a certain volume, we consider a three-dimensional object. Suppose here we consider a cube. Now in this cube, the total volume is V, the total volume of the cube is V, and the total charge Q is uniformly distributed on this conductor or in this volume. Okay, we consider the volume of this cube to be V, which is a conductor, which we consider to be a conductor here, and Q is the total charge which is distributed over this volume. Now in order to calculate the charge density, we will have to determine the volume charge density. Okay, now according to the volume charge density, what we'll have to do, we'll have to divide the total charge. Since this is a uniform distribution, so we have to divide the total charge by the total volume. So what we get is rho, which is the volume charge density. if we consider a small volume element here, thus volume is delta V. We consider a small volume element here whose volume is delta V, and in that volume element the total charge present is delta Q. Okay, the total charge present in this volume is delta Q. Now if this is the case, if we consider this small volume, the shaded part, then what will be the charge density for that part? It will be delta Q divided by delta V. Okay, now if that volume element dV is very small, or we can say we can consider that if this element is very small, then this delta V can be replaced by dV, and delta Q can be replaced by dQ. So for in that case, if this volume element is very small, infinitesimally small, then what we will consider? We will have to consider dQ and dV, right? dQ is the charge present in that volume, and dV is a small volume element. For that element, the charge density will be dQ divided by dV. If we cross multiply these two quantities, then what we will get? We will get total charge present in that small volume element. That will be equal to rho into dV, right? And what will be the unit of volume charge density? That will be Q divided by volume. So for charge we have coulomb, and for volume we have meter cube. So what will be the final unit of volume charge density? That will be equal to coulomb per meter cube. Okay, so these are the three charge distribution that we can study, or if we have to calculate, or if we have to determine the charge present on any conductor, then we can easily study the distribution using these three distribution rules. Okay, so first was the linear charge distribution, second was surface charge distribution, and the third is the volume charge distribution, right? So these are the three distribution ways. Next, we will have to determine the electric field due to a continuous volume charge distribution. Before, we used to calculate the electric field due to a point charge, right? So in this diagram, I have drawn a point charge here. At this point, there is a point charge, and due to this point charge, we used to calculate the value of electric field intensity at this point, which is at a distance r from O. This is any arbitrary point. Okay, so we used to calculate the total electric field intensity at any point due to a point charge, right? So what was the formula for electric field intensity? That was kq divided by r square, where k has a value 1 by 4 pi epsilon naught. Similarly, here we will have to calculate the electric field due to a continuous volume charge distribution. So here we have to calculate the electric field intensity at any point. Similar to this diagram, we have considered a point, any arbitrary point P, which is at a distance r from this volume charge distribution. We have said here volume charge distribution. So this is the volume charge distribution. That means we have considered here a volume where whose volume is V, total volume is V. Here we have considered the volume to be capital V, and the charge Q is uniformly distributed over this conductor. Okay, we have considered the volume charge density to be rho here. Okay, for this distribution, the volume charge density is rho. Now, what we'll have to calculate? We'll have to calculate the electric field intensity at this point due to this volume charge distribution. So, in order to calculate that, we will first consider a small volume element here, right? So we have considered this small volume element to be delta V. Okay, now what is the total charge present in this small volume element? That is delta Q. Okay, so delta Q is the total charge present in this small volume delta V of the conductor, of the volume that we considered. Okay, now what will be the total charge of this part of this volume? That will be equal to rho into delta V, since rho is the volume charge density and delta V is the volume. So what will be the total charge in this small volume? That will be equal to delta Q, which is equal to rho into delta V. Okay, this is the total charge present in this small part or this small volume. Now what will be the electric field due to this small volume element at the point P? right? So we will use the similar formula kq divided by r square. Here r is the distance of separation between this volume element and the point P. Okay. Now what will be the value of q? We will have to put the value of q as delta q in this for this part, right? So what is the value of delta q? Delta q is rho delta v. So we have put here rho delta v divided by denominator r square. So we have the denominator as r square. In the next step, what we have written is we have written the same formula in the vector form. We have put a unit vector r cap in this part, right? So now this is the electric field at this point due to this small volume. Okay. Now what we'll have to consider, what we'll have to calculate is the total electric field at this point due to this whole volume. So for this whole volume, we may simply consider this volume to be made up of small volume elements. Okay. Now for each volume element, we consider the volume to be delta V. So if we sum up the electric field intensity value for all those small volumes, then we will get the total electric field intensity at this point. We have done the same thing here. What we have considered here is we have considered small volume elements whose volume is delta V. Okay. Now we will have to sum up the electric field intensity value due to all those volumes, okay, which acts at the point P. So here we have for in terms of K, we have put here 1 by 4 pi epsilon naught, which is the constant. I have put a summation here, summation over all V, all delta V, all the volume elements we have summed up, and this is the electric field value for this whole volume. So this part comes here, rho delta V divided by r square. So what is this? This is the electric field intensity at this point due to this whole volume, and we have considered this whole volume to be made up of small volume elements, each of whose volume is delta V. Okay. If we write this formula in vector form, then similar to this formula, we'll have to put a unit vector r cap in this place. Okay. So what we have done here is we have calculated the electric field due to a continuous charge distribution, where we have considered a volume charge distribution, and for that volume charge distribution we have calculated the electric field intensity at a point P, which is at a distance r from the volume. Okay. Thank you.